Hi guys, welcome back to another video. This video is going to be about exponential functions. We'll start off with the equation for exponential functions, which is y equals a times b to the power of x. Listed below, I have all of the variables. So a stands for the initial amount. On the graph, that initial amount will represent your y-intercept. B represents either your growth rate or your decay rate. T represents time. The variables can also be interchanged with N or X. So any of those three letters will represent time. And then Y is the value after T time. And we already know that Y can also be represented as f of x. So they can say f of x or y, and that will both represent the value after an extended amount of time. So you can have either exponential growth or exponential decay. And the way to tell them apart is to look at the rate. So if b is greater than 1, then you're going to have exponential growth. But if b is less than 1, then you're going to have exponential decay. And I have some examples there listed of real world examples. So an example of exponential growth would be like bacteria growth, or we saw it especially during COVID where, it just grew exponentially and then everybody had it. And then exponential decay, decomposition, or depreciation of a car. So you probably haven't bought a car yet, but when you do, you'll learn that as soon as you drive off the lot, your car is already worth a lot less than what you paid for it. And the more you drive a car, the less it's worth. So that decreases in value exponentially. So the main equation for exponential functions is y equals a times b to the power of x. But you can also use this formula here. So depending on whether you're going to have exponential growth or decay determines if you're going to be adding the rate or subtracting the rate. But basically the whole 1 plus r will represent the b, and the whole 1 minus r represents the b. Okay, but when it's plus r, it's going to be growth, and when it's minus r, it's going to be decay. Okay, but that's basically getting plugged into this b into the formula. So the rate will either be, you're adding the rate or subtracting the rate depending on if it's growth or decay. So let's start with some examples. You have a bacteria culture starting with 30 bacteria that doubles every hour. So what I like to do first off is just underline and annotate the problem on what is important. So I see that it says it's starting with 30 bacteria. That will be my initial amount, which is the letter A. So A is 30. And then it says it's doubling every hour. So doubles would be the rate. And if it's doubling, we're going to be multiplying by 2. And then every hour would be x, but it doesn't tell us for how many hours. So that can go on forever. So we just don't know. Okay. But we have a table here, and we're going to calculate how many bacteria there are after 5 hours. So the number of hours will be represented by the variable x. The number of bacteria, it will be y. So at 0 hours, we started with 30 bacteria. If we double 30 times 2 will be 60. So there are 60 bacteria after 1 hour. 60 times 2 will be 120. 120 times 2 is 240. 240 times 2 is 480. 480 times 2 is 960. So you take every previous value and multiply it by 2 because the bacteria are growing by a factor of 2. So they're always being doubled. Now this little grid here, we're going to use it to represent the graph of this exponential growth. So on the y-axis, I'm going to have the number of bacteria. And on the x-axis, I'm going to have the number of hours. And it's kind of tight here, so I'm sorry. So there were 5 hours, so 0, 1, 2, 3, 4, and 5. Now, for the number of bacteria, we have to go to at least 960 since that is the highest number. So I think what I'm going to do is go by increments of 60s. You can also go by increments of 50s if you want, 50, 100, 150. Or you can do hundreds, 200, 300, 400. There's no wrong answer as long as you're constantly adding the same number every time. What you do not want to do, which is a mistake that some students make, is grabbing these values and then just writing them here like this. So that would be incorrect because these are not being added by the same number every time. So this would be wrong. So you have to add, you're either going to go by 10s or 20s, 50s, 100s, whatever your increment that you decide, but it needs to be adding the same number every time. Okay, so with that being said, I'm going to go by 60s. So I'm going to do 0 to 60 plus another 60 is 120. Plus 60 is 180, then 240, and then 300, 360, 420, 480, 540, 600, 660, 720, 780, 840. And so you can see I ran out of space there, but I could keep going. So another 60 would be 900, and then another 60 would be 960. And so that's the maximum we needed. So we're a little off the grid, but that's okay. All right, so at 0 hours, we have 30 bacteria. So that's half of 60, so that'll be right there. After 1 hour, we had 60 bacteria. 2 hours, 120 bacteria. 3 hours, 240 bacteria. 4 hours, 480. And then after 5 hours, there were 960, which is up here off the charts, like we said. So I'm just going to follow the points to make my graph. And at the end, I will be putting an arrow because it didn't say when it stopped growing. So this can keep growing on forever and ever and ever. Okay, so part B says create a function to represent the growth of the bacteria. So we're going to look at the formula that we have up here, which is y equals a times b to the power of x. And I can rewrite y as f of x. So I have f of x equals a times b to the power of x. Well, earlier in the problem, we said that a was 30 and b was 2. So I'm going to have as my equation f of x equals 30 times 2 to the power of x, because x we can substitute as many hours as we need. And that's what we're going to do in the next problem, where it says how many bacteria will there be after 10 hours. Well, that 10 hours is going to represent our time. Okay, so in this previous problem where we had set up the formula, since now x is 10, in this x and on that x, I'm going to replace a 10 in there. I'm going to plug in 10 hours so we can see how many bacteria there are. So that'll be f of 10 equals 30 times 2 to the power of 10. And so what you're going to do is type that into your calculator. (30 times 2 to the power of 10 is equal to 30,720. Bacteria. Okay, so that's the answer. So you can see that it grows very, very quickly, because at 5 hours, we didn't even have 1,000 bacteria, but just after 10 hours, we're already at 30,000. So you can see that grows very quickly. So there are a lot of ways you can tell that it's exponential growth. The first thing you can look at is that b is 2, which means it's greater than 1. And remember, if b is greater than 1, you have exponential growth. Additionally, you can see that the graph is increasing, which is going up, which represents growth as well. And on top of that, it does tell you in the question as well that it's bacterial growth. So you will have a few indicators on whether or not you're dealing with exponential growth or decay. All right, so moving on to the next example. Each year, the local country club sponsors a tennis tournament. The tournament starts with 128 participants, and during each round, half of the players are eliminated. So let's go and underline the important pieces of information. So it does say it starts with 128 participants. So your initial value is represented by the variable A. And then it says during each round, half of the players are eliminated. So that will represent B. And if we're getting rid of half, then B will also be 1/2. Okay, so now we're going to complete our table. So it did say that at 0 rounds, we started with 128 participants. So if you multiply 128 times 1/2, you get 64. Now multiplying by 1/2 is the same thing as dividing by 2. So I can do 128 divided by 2 and I would get the same answer. So it kind of just makes it a little bit easier to just say divided by 2 as opposed to multiplying by 1/2, but either will be acceptable here. Okay, so 128 times 1/2 is 64. 64 times 1/2 is 32. 32 times 1/2 is 16. 16 times 1/2 is 8. And 8 times 1/2 is 4. Okay, so we're going to graph this again. So the number of rounds will go on the x-axis and the number of players will go on the y-axis. So I'm going to label my axes now. So number of players versus number of rounds. And we have up to 5 rounds right now, but that doesn't mean it stops at 5. And then I need to get to at least 128 because that is the biggest number. So we could go by 10s or we can go by 20s. But I have found that 16 would be the best number just because 16 is divisible by all of the numbers on our table. But if you were to choose like 10s or 20s, you would just have to kind of approximate in between, like it won't be an exact point. And what I mean by that is like, let's say we had, if you went by 10s, then 4 and 8 you would kind of have to approximate it somewhere in the middle, which is totally fine. There's nothing wrong with that. But I'm just going to pick a number that's divisible by my coordinate point, which is 16. So I'm going to add by 16 every time. So 16 plus 16 is 32, plus 16, 48, plus 16 will be 64, plus 16 is 80, and then 96, 112, 128, and 144. And we have some extra space above, but that's okay. We don't have to use the whole graph. Okay, so at 0 rounds, we started with 128 players. After 1 round, we had 64 players. After 2 rounds, we had 32. 3 rounds, 16. 4 rounds, 8. And after 5 rounds, we had 4 players. Okay, so now I'm going to connect the points to make my graph. And I'm going to draw an arrow on the end of that because time is going to, well, the number of rounds can keep going on. Okay, so some indicators that this is an exponential decay problem. So B is a fraction, meaning that it is less than 1. So if B is less than 1, it's decay. And then you can see in the picture that the graph is decreasing. Okay, so part B says create a function to represent the number of players in the tournament. So we'll start off with that parent function, which is f of x equals a times b to the power of x. So we rewrite the equation, plugging in our a and b. A was 128 and b was 1/2. So the equation is f of x equals 128 times 1/2 to the power of x. Letter C says how many rounds will it take to determine the winner of the tournament. So when it says how many rounds, round is being represented by the variable x. Okay, So if they're asking how many rounds, they want us to solve for x. So that is the unknown variable. We don't know what x is. And then it says to determine the winner. So winner would correspond with the number of players. So if you're the winner, that means you're the last person playing. So how many rounds will it take for y to reach one person? Because there can only be one winner, okay? So the winner means y equals 1. So they're asking when y equals 1, what is x? Okay, now y is the same thing as f of x, right? We talked about that at the beginning. So what I can do is plug f of x equals 1 into this f of x, and then I can solve for x, which is a number of rounds. So I'm going to plug in 1 equals 128 times 1/2 to the power of x. Okay, and now I'm going to use algebra to solve for x. So you can use PEMDAS, and you're going to use it from the bottom and then work your way to the top because you're solving for a variable. So first, is there anything you can add or subtract? The answer is no. Is there anything we can multiply or divide? Yes, we can. We can divide out this 128. So these will cancel out. So now what I'm left with is 1 over 128 is equal to 1/2 to the power of x. Now, you probably have never seen a type of problem like this where x is an exponent that you're trying to solve for. So what you have seen is, like, let's say it's a squared and then you do the square root to cancel out the exponent, or the same thing if it's a cube, then you take the cube root and cancel out the exponent, or you know, some variation of this, but you've never done it where the variable is x. So what you cannot do is the x root. Like this is not a thing. You can't do that because what you do to one side, you do to the other side. So it will cancel here, but then you're stuck with x outside of a square root here, which makes the question a lot more complicated. So what you're going to do to solve is take the natural log of both sides. So I'm going to make a little note, and then I'm going to show you how it works. So you're going to take the natural log of both sides to bring the exponent to the front. And you can pause that and copy the little memo. But what you're going to do is multiply both sides by the natural log. And that's an L and like the letter L for logarithm. So you're going to multiply both sides and put everything on each side in parentheses. So what happens on this side is that you just end up with the natural log of the fraction 1 over 128. But on this side, what happens is that the exponent of x is going to come to the front of the natural log. So now we have x times the natural log of 1/2. And what that does, it helps us because now instead of x kind of floating in the air, you can see that it's on the same level as everything else, and now you can actually solve for it. Now, this natural log stuff might look very scary and intimidating. You probably haven't seen it before. There's letters, it's weird. But the natural log of a number is still just a number. So I'm going to prove that to you now. So let's say we have the natural log of 1/2. Okay, just kidding. Sorry, I have to convert it to a decimal. So the natural log of, wait, I messed it up. The natural log of 1/2. Oh yeah, it's the same thing. All right, so it's just a decimal. Excuse me, negative 0.693147. So it's just a decimal. Excuse me, I need to drink water. So it's just a decimal. So instead of writing this repeating decimal, it's just easier because look how the numbers don't even stop. So if you're in your calculator, you can highlight your previous answer, and if you press enter, you'll get a bunch more digits, because the calculator rounds it for you automatically. And this is also still rounded, so this decimal actually keeps on going forever. So we use the natural log to represent really long decimals like this, but all this is to say that the natural log of a number is still just a regular old number. It's just a really long decimal. So using PEMDAS, if you have, so if this is a number, this is a number, right? Number, that's the number symbol. If you have a number being multiplied by your variable that you want to solve for, to undo multiplication, you divide. And that's the same thing we're going to do here. We're going to divide out the natural log of 1/2. And these two will cancel out because anything divided by itself equals 1. And then so x will be equal to this really long fraction. So we're going to put that in the calculator now. So the natural log of 1 over 128 over the natural log of 1/2. And we get the number 7. So x equals 7. So it takes 7 rounds to get a winner. Now some of you guys are probably able to do this with the table. So if you finish the table, you can go 6. And then if we're splitting it in half, then after 4 would be 2, and then 7 rounds would be 1. So you could do it this way, but it won't always be this easy to continue the table. So that's why it's important for you to understand how to take the natural log of both sides, especially because we're going to be using it a lot in the next lesson. So just to recap, you use the natural log to bring down any exponents that you need to solve for. Okay, so here are some definitions, some financial definitions, because we're about to do compound interest. The principal amount in financial formulas is the balance upon which the interest is paid. The simple interest is the interest paid on your investment or your principal amount, but not on any interest that has been added. And then your compound interest is the interest paid on both your principal amount and on all the interest that has been added. So it's a little bit confusing, but let's do some real life examples. Before we do that, I'm going to start with the formula. So this is the compound interest formula. You do have access to this formula on your formula chart. It is A equals P times 1 plus R over N to the power of N times T. So A is the accumulated balance after Y years, also called the future value. P is your starting principal or the present value. R is your rate. I put here that you need to express it as a decimal. That is very, very important. So the question will usually give you a percent, and then you have to convert it to a decimal. The formula will not work if you put a percentage in there. So let's quickly review how to convert between percents and decimals. So let's say they said 35%, okay? So what you do is you grab the decimal from the back, and you're gonna move it 2 places to the left. So that means that 35% is the same as 0.35. Okay, let's do another one. If they say 7%, you always put the decimal on the back, and so you're gonna move it over 2 decimal places. Now, if there's a little space missing, you're gonna fill it in with a 0. So 7% is the same thing as 0.07. Now, what if they gave you something like 1.64%? Okay, so you're not gonna put the decimal in the back over here. Rather, you're gonna start where the decimal already is, and you're gonna move 2 places to the left. So 1.64 will be 0.0164. Okay, so I always have to move it 2 places to the left. Okay, and then T is time expressed in years, and then N is the number of compounding periods per year. So there are different compounding periods that they can ask you about in the question. So I'm gonna put all of the different words. So these are all gonna be related to N. Okay, so they can say yearly, quarterly. Actually, they can even say biannual. Let me see. Quarterly, monthly, weekly, and daily. So all this is referring to is how many times do these things occur in every year. So how many years are there in 1 year? The answer would be 1. Biannual means it's happening twice a year. Quarterly, if you divide the number of months by 4, wait, I messed that up. Well, quarterly is 4. Quarter, in quarters. Anyways, monthly is 12. There are 12 months. There are 52 weeks in a year, and there are 365 days in a year. Now, these words will not have the number attached to it in the question. It is up to you to memorize these words and then the number that is attached to it. So if it says, we're compounding this monthly, then you have to know, 1, that represents the letter N, and 2, that monthly represents the number 12, okay? So just have those in the back of your mind. Let's start some examples. So you deposit $5,000 in a bank account that pays a rate of 3% and compounds interest monthly. How much money will you have after 5 years? Compare this amount to the amount you would have if interest were paid only once each year. So I always like to start by underlining the important things or highlighting. So the first thing is you deposit $5,000. So that's your principal, your starting principal, which is the letter P. So that's what you start off with, okay? And then it says it pays a rate of 3%. But remember, your rate has to be a decimal. So what we're going to do is convert it by moving the decimal over 2 places, which would put it at 0.03. And then the next thing it says it compounds interest monthly. So that's a compounding period, which represents the letter N, and then monthly would be 12. Okay, and then it says after 5 years, so that will be obviously T, so T is 5. But then the question kind of changes a little bit, because then it says compare this amount to the amount you'd have if interest were paid only once each year. So the variable that is changing here is your compounding period. So instead of it being compounded monthly, it'll be compounded annually, because it's once each year. So that means that now N will be 1. So we're going to have 2 different equations happening here. So I'm going to start off by writing the formula, which is A equals P times 1 plus R over N to the power of N times T. And I'm going to plug in everything that we have. So A equals 5,000, 1 plus 0.03 over 12 times, to the power of 12 times 5. Okay, so that's for the purple one. And then we're going to do versus, because then the problem changes to N equals 1. So everything else is going to stay the same, but N is now going to be 1. So we have 5,000, 1 plus 0.3 over 1 times 1, to the power of 1 times 5. So what I'm going to do is just put these straight into the calculator. So we have 5,000 times 1 plus 0.03 over 12 to the power of 12 times 5. Press enter. You get 5808.08. So that's for the purple one. And this is a dollar amount, so make sure you put your money symbol. 5808.08. And then now let's do the pink one. So it'll be almost exactly the same, except that the 12 would now be a 1 because we're doing it annually. And that amount is 5796.37. Okay, so you can see that the difference is not that big. We can subtract them in the calculator. So we have this one minus the smaller one. So you're really only getting like $12 more, $11 and change. So it's really not that large of a difference if you're compounding monthly versus annually. But you do get, 11 more bucks. So something is something. Okay, let's try another problem. Your grandfather put $100 under his mattress 50 years ago. If he had instead invested it in a bank account paying 3.5% interest compounded yearly, roughly the average U.S. rate of inflation during that period, how much would it be worth now? So always start by highlighting or underlining the important pieces of information. So he started off with $100 under his mattress. So that's going to be our starting principle of P. So P is 100. 50 years ago, that's going to be your time. The interest rate, which is 3.5%, that's going to be 0.035. And then it says compounded yearly. So that would be a compounding period, which represents the letter N, and yearly is 1. So how much would that be worth now? So I always start by writing the equation, and then I just fill in the variables that we have. So A is equal to 100, 1 plus 0.035 over 1 to the power of 1 times 50 for 50 years, okay? And let's go put this in the calculator. Sorry. 100 times 1 plus 0.035 over 1 to the power of 1 times 50. And that amount is $5.58 with 49 cents. Now notice that I only have 2 decimal places because this is a dollar amount. You have to account that money is only ever written with 2 places after the decimal to represent your coins, like your pennies and your dimes and your quarters and all that. So you should only ever have 2 decimal places. So even though the problem was 493 as a decimal, we're not going to write all 3. You're only going to write the 2, cents. If it rounds up, then you can round up the last digit. So if it's 5 or up, then you round up, okay? But in this instance, it stayed the same because 3 is less than 5. Okay, so these are the compound interest when you have compounding periods. The next page is for continuous compounding. So if it says the word continuous, that's going to be an indicator that you're going to be using this specific formula, which is an equation I like to call the PERT, because it looks like it says PERT. So A equals P times E to the power of R times T. So A is your accumulated balance after Y years, P is your starting principal, R is your rate, which still needs to be expressed as a decimal, so still convert the percentages. And then T is the number of years. Now, you might notice that the only letter that is missing is the letter E. The letter E is not a variable. It's similar to pi. You know how pi equals 3.14? So if I put pi in the calculator, hey, why didn't it give me the number? Let me try that again. Okay, it's not giving it to me for some reason. That's weird. Let me see. I'm like not that comfortable using this app. Symbols. Pi. Will they give it to me now? Okay, no. Well, pi is like 3.14. It's not wanting to give me the decimal for some reason. Now, if we put e, where did I get that again? Here? Okay, so e is right here. So if I were to select the letter e and press enter, oh my gosh, it's not going to give it to me. How do I make it give it to me in a decimal? Okay, it's not going to give it to me. So let me just Google it and I can show you. Okay, so the letter E in math is approximately equal to 2.7182183. So it's just like pi. You know, pi is 3.14. So it's like this, look. So E is just a really long decimal. But it's just 2.71, and you can see it goes on forever and ever and ever and ever. So all that to say that E is just a number, and E is 2.71, etc., etc., etc. So there is an E button in the calculator. Please do not type 2.71 instead of the letter E, because you will be cutting the decimal pretty short. So if you start cutting the decimal, then it's not going to be an accurate answer. All right, so let's try some examples. So you deposit $100 in an account with an APR of 8% and continuous compounding. How much will you have after 10 years? So you deposit $100. That's going to be your starting principal. If you have an APR of 8%, then your rate would be 0.08. Now the keyword here being continuous compounding. That's going to let you know the formula that you're going to use, which is the PERT equation. Okay? And then how much will you have after 10 years? That will be your time. So we're going to fill everything in. So I have A equals 100 times E to the power of 0.08 times 10. Okay, now I'm going to type that into the calculator. 100 times E to the power of 0.08 times 10. And you get 222.55. Remember, you're only putting 2 decimal places. Okay, last example. Suppose you put money in an investment with an interest rate of APR equals 3% compounded continuously and leave it there for the next 18 years. How much would you have to deposit now to realize $100,000 after 18 years? All right, so key features here. Interest rate of APR 3% means that your rate is 0.03. Compounded continuously lets you know you're going to use the PERT equation. 18 years will be your time. And how much money, let me move this down. How much money would you need to deposit to have $100,000? So that $100,000 is what they want to have at the very end. And they want to know, what do I have to invest up front to get that amount after 18 years? So this will be 100,000. Let me get rid of the comma actually. Equals, and we don't know P, times E to the power of 0.03 times 18. Now we already talked about E being just a number. So if I put E times 0.03 times 18 in the calculator, I get a decimal 1.71. Again, if you go up and highlight that previous answer and press enter, you can see there's so many more decimals, but the calculator rounds it for you. So to eliminate a rounding issue, you just want to keep it as e to the exponent, because if you round in the middle of your problem, you will get the answer wrong at the end and you'll be off by like a little bit. So to avoid that happening, just keep it as e to the power of whatever. Now, we already talked about this being just a number. All of this is a number. And when you have a number being multiplied by a variable that you want, to undo multiplication, you're going to divide. So we're going to divide both sides by e to the power of 0.03 times 18. On both sides, these will cancel out. So you're left with p on the right-hand side. And now in the calculator, we're just going to type all of this. 100,000 divided by e to the power of 0.03 times 18. Now, you see how there's only one decimal place, but we've talked about how we need 2 places after the decimal when we're talking about money. So what you do is highlight your previous answer by clicking the up arrow and then press enter. And now you can see that there are a lot more digits. Now the decimal is 825, and I only need 2 places. So it could be 82 cents, but that third number is a 5, and rounding says if it's 5 or greater, you have to round up. So instead of 82 cents, it's going to round up to 83 cents. Okay? So P is equal to 58,274 with 83 cents. Okay, so just to recap, if it says the word continuous specifically in the problem, so it needs to have the word continuous, you're going to use the per equation. But if it gives you a compounding period, such as monthly or yearly, then you're going to use this longer formula that has the compounding periods. Okay. Other than that, it'll either be exponential growth or decay. So just to recap, if your rate is greater than 1, it's growth, less than 1, it's decay. You can also use these formulas. Those are very important as well. And the reason that it's 1 is because you always start with 100%. So from 100% of what you currently are, you can add a rate. So you're going to get bigger. Let's say you get 35% bigger. Or you can also decay, right? So you can lose, let's say, 35%. But what that means, 100... Remember, you can have percentages in the formula. So 100% as a decimal, if you start out here and you go 2 places, you end up with 1.00 or just 1. So that 1 is referencing you starting at 100%, and then you're either adding on to that or you're subtracting from that, whether it's growth or decay. So that's why you need to pay attention to that 1. But yeah, so I hope you understood the lesson, and feel free to leave comments if you have any questions, and I will be happy to clarify. Okay, I'll see you guys in the next video. Bye.